So that sort of thing. Again, I'm not here, I'm not a detector, or I'm not gonna send you to honor court, hopefully not. But it's good for you if you really don't know the answer like homework, don't write anything, just submit it blank. You know, like having some honor for yourself, not the teacher. That's just what he says. And funny thing is, one of those students who did the problem in the midterm, the cylinder tube fluid viscosity, I went to his homework and he did not do the cone problem. He was not able to do the cone problem, which makes sense. Because the cone problem is 1,000 times harder. All right. So please try to be consistent. To be honest with you, say, I know a lot of you guys work, and that's fine. But this course requires a lot of work. We only have 50 minutes. This course should be 1 hour 30 minutes, twice a week. This course is only 50 minutes. You know, the people who scheduled this course didn't respect the course. But please, you as a student, please, you respect the course. That means when you go home, I know you work, but you have to really make time for this course. You have to practice. Yeah, when you go home, you have to either go to library at home, grab your book, pick some problems, start work on it. If you don't know the answer, just like a few of you regularly come to my office, which is fine, I like it. We go over it on the office, don't leave it like that. Now, I'll break the homework soon, and I'm not gonna put it on a curve. So it's gonna be just a straight. And the trend is like, before I grade it, I know the trend. We have some hundreds, like perfect grades, 100 out of 100. And then we have people like 5 out of 100. In fact, or 0. I just give them +5 for just coming to the test and submitting something. Because there should be a difference between those people and those who didn't show up, right? If I give 0 to both of them, that's not fair. So we have this trend, and you know, it's like a lot of hundreds, a lot of zeros. And maybe 1, 70, 80, or maybe 2. It's just very weird the way it works. It should not be like that. It should be like a lot of 80s, 70s, and then a few hundred, and then a few zeros. That's the way it should be. All right, now let's go back to our discussion of conservation of mass. And we started with something called divergence theorem. This was our form. I'm not going to write divergence, I'm going to just write the partial T rho dV, conservation of mass, plus integral rho v dot n ds. So this was conservation of mass we derived, and we started with just first principle, which is the mass of a control volume is always the total derivative is 0, and then you use this concept of total derivative is inside the local derivative cross the one that crossed the border, the mass that's leaving or coming in. And this was principle of conservation of mass. And we also simplified for different versions. For example, when you have sum of rho VAs is equal to 0, when you have constant velocity profile, constant velocity profile. So when you expand this integral, first of all, this is 0, it's a steady state, constant velocity profile, a steady state. So when you say steady state, that means versus time, no derivative. So this entire thing is 0. And then this integral, when you expand over the faces of this volume, m1, m2, m3, and so on. If we assume this velocity, variation of this velocity over each phase is just constant, we can take these two, this out of the integral, and also constant density, or incompressible. Or aka incompressible. So for this assumption, which is usually this three assumptions, steady state, constant velocity profile, and incompressible. These three assumptions usually happen in our field, mechanical engineering, the slow speed flow. Some of these assumptions does not meet in aerospace engineering, but in mechanical engineering, most often they do. So for this assumption, you get rid of this integral, and for that, because it's incompressible, the density is constant, take it out, and then v dot dn, v dot nds over each face is the integral, but because the velocity is constant over that face, not the entire field, over just that face. The velocity may be different here, 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 but over this face is constant. You take it out of the integral, so you'll end up with this equation. Also, the sum of the fluxes or mass flux, later we define the flux term precisely, but right now just take it as granted, like this is mass m dot, mass rate. The sum of mass rate is 0. Now, you know that if also the density is constant, incompressible, you can take it out. So this is compressible, this compressible. Because you didn't take this out of the integral. Now, if you take it out of the integral, density everywhere rho the same. It just non-zero times rho is 0. What? That means this term is 0. That means v a dot a sum 0. So this is for constant density. So this one is more general. When the density is constant, you take the rho out and you get that. And then we name this as Q or volume rate. And then we solve a bunch of problems. But every time I give you a problem, you have to start from here and make assumption. Is it a steady state? Yes, get rid of that. Go next one. Is the velocity constant over the profile? Is the density constant? If the density constant, you can take it out, right? But if it's not constant, you have to take it inside this summation. So then you end up with that. This will finally, like everything, if all assumptions hold, this is the most simplified version. That means the volumetric rate of the flow coming in is the volumetric rate of flow leaving out. And we solve some problem. Now let's go back to the way that the book is showing you the same thing we did. And we have something called Reynolds transfer theorem. So this is the similar approach using Reynolds transfer theorem that they just say the same thing. The local rate of change over the volume. So this is eta is like anything. Like it could be mass, just the way I said. We had a box placeholder. You would place anything in it like mass, momentum, energy, and then you get different conservation costs. This just like that. Times plus the net flux passing through the surfaces, call it convective, from convection, the movement of fluid, is equal to the total rate of change. So we call this Reynolds transfer theorem. And we actually proved that using divergence theorem. So we not only we take it as granted, but also we proved using divergence theorem that you can write, this is a surface integral. You can convert that to volume integral using divergence theorem. And then we end up with an equation like this, differential form. Partial rho partial t plus divergence rho v is equal to 0. Now the way this book does, it doesn't show you everything in one point, which is, this is the way it should be. Because these are, if you see everything in one point, you say, aha, okay, this is not really distracting me from the concept. The way the book does this is he makes one chapter for that, so he starts from scratch, not starting from here, and he takes an infinitesimal element. So this is like dx, dy, and dz and dy. And for that, he uses like calculus very approximate crude character, which is not accurate in general. And then he drive that, and it's like 20 pages derivation. This chapter 7, if I'm not mistaken. We don't need to do that. We just start from that. We already showed that. And we apply divergence theorem, we get that. This in the notes, lecture notes, previous classes. Now all we need to do is just solve some problems, some numerical problems, because we know how it's derived. Now, for this problem, again, you can apply this assumption. What if I have a steady state? For this is differential, call this differential form. Differential form. They call this integral form. Right? Both are same thing, but this is for a big volume, macroscopic. This is for point-wise, microscopic. So these are the same thing, but written for different control volumes. Now, for example, I can do the same thing for differential form, which is chapter 7. So if I have a steady state, what do I get for that? If steady state, what do I get? 0. So for a steady state, again, divergence rho V is equal to 0. This is called a steady state conservation mass. The conservation of mass, or continuity, or AKA continuity equation. Now, if it's incompressible, what do I get? When the density is constant, can I take this density out?
Yeah.
Yeah, so you get what? Divergence of velocity is equal to 0. Add to this plus constant density or incompressible. Constant density or incompressible. So as you can see, the most simplest form, this is the simplest form. In differential form, it's called divergence velocity is equal to 0. This is the simplest form in differential form. The simplest form in integral form is sum of the volumetric rates are 0. These are same equation. Now the way the book does, he has one chapter for that, one chapter for this. Why? I mean, this can be beneficial to learn, but also it's distracting. The student may think, okay, this is a different thing. This is totally different. No, they're just the same. If you follow the divergence, that's the reason I'll teach you divergence here, which is not in the book. Because if you know that, you know all these are just convertible. You can start from here and convert to that. Right? So now, after this, we go to the next one. One thing I want to talk about here is velocity profile. And as you can see, we had, I want to draw it here. But we need to have a little bit more white. So we had an example like, we had a tanker and we had 2 inlets. And usually the way you see it in the drawing, when they engineer the make drawing, you see something like V2, let's say V1, V2, and call this V3. They show it just like that. But look, in the real life, if you have a good camera, if you can zoom on this cross section, in that cross section, so I'm going to draw that here, zoom. What you have is this. This is the upper one, this is the lower one. And the velocity is not constant. The velocity is like 0 here, 1. Why? Because it's what? It's a viscous what? And you have a sudden increase in the velocity, and then go back like this. That's the velocity profile. The velocity profile, when we say constant, it's not actually constant. There is a, because it had to go to zero. There is no way on the wall, it must go to zero. So the velocity is almost constant here. Again, you have some variation, but roughly constant here, but zero here. Now you may ask the question, why do I get just one row ahead? It's a constant. The answer to that is, assume the fluid doesn't have any viscosity. Zero viscosity, what happens? Yeah, if it has zero viscosity, what happens in the wall? There is no attachment to the wall. The flow goes everywhere. Imagine, this is not going to happen in real life. But imagine there was no viscosity. This was okay. The flow would pass through this outlet just with constant velocity. Why? Because it doesn't even feel the wall. Why? Because the only way to feel the wall is to have viscosity attachment. So, for most gases like air and like hydrogen, this assumption is a good assumption. As long as you don't have this, you don't want to consider this area in detail. So your velocity profile is almost constant. But for fluid like honey or oil, for a small cross section, this assumption is not valid. So you have something like parabolic profile. In that case, imagine the fluid was not ideal. Then what you have is like this. So here, it says something we call V core, or core velocity, the velocity at the very center of the core, and then it's zero on the top, zero on the bottom. Now, if you put your coordinate system here, this is the y. So y is 0 here, y is equal to some distance, call it r, or you can just call it anything, a. So the velocity profile in this case is written to u versus y is equal to v at core times 1 minus r over r squared. Is a parabolic velocity profile. You can see that if you plug r, and this r is in fact y. If you plug y is equal to r, what do you get? R divided by r, 1. 1 minus 1, 0. If you plug y is equal to 0, what do you get? 0 divided by r, 0. 1 minus 0, 1 times VC, V at core. So you get this velocity profile. Second order parabolic. You may have third order. These are just approximations. But this is more real when you have oil or honey, a very viscous fluid in a small diameter. But if you have a very large diameter or gas or something, you can say the slope here is so sharp that you almost see a constant. Just like here. I'll show you here. V constant. In that case, V core is just the same. But if I give you this profile, if I say the fluid is viscous, that means you have this, you can't just start with this form. You have to go back here and take the integral. Why? Yes, because it's changing the velocity.
Is that also dependent on speed?
Yes, that's the speed, that's the core velocity. So if you have more core velocity, you see the shape, this is the shape, the correction factor. The shape is same, but velocity increases, the core velocity. Alright? So this is just a hint about, when I give you a problem, you should always ask, is this the viscosity effect important? And if it's important, you have to take the second order parabolic relation, and then you can't start from here. You get a 0. You have to go back, and again, is it a steady state? Yes, 0. Here, is it incompressible? Yes. Take a while. But is the velocity constant? No. The velocity in that case is not constant. So instead of this form, you have to have this. Integral v dot n ds over surface 0. For the constant velocity, you get that from out of this when you expand the integral. make sure you don't make these mistakes in the test. Now, next question here, it says, it's one of the problems in the book. It say you get a water hydrant, and it got two. Now we need to have dim the light. You already solved a few problems. The participation is not good today. So here you have a water hydrant, and the diameter at different points are given, as you can see. Let me see if I can zoom here. There you go. Here is 75 millimeter. The velocity also given. Now every time velocity given, like just one data like that, is implying that it's most likely a constant. That means the flow, either the diameter is so large or the fluid is not very viscous in that velocity. So the parabolic effect is not as strong. So you always have a constant. So at this point, also the velocity is given. As you can see, the flow rate is given at C. So at this point, the flow rate is given. And then the velocity at the point A is also given, going out. So the flow comes from the earth, and then it goes at B and A. But they are not symmetric necessarily. Here, this 75, the one on the right is 100. And what they're asking you is to find the velocity that is exiting the pipe at point B. Right? So you have this velocity here, diameter here. Even if you don't have diameter here, velocity, you can use this. The definition of Q, here you find Q is equal to VA. So if they give you volumetric rate, all you need to get the velocity divided by A. So to solve this problem, first we actually find the velocity at point C, which is here. So the volumetric rate is given 0.15 meter cube over second. You divide by the diameter here at point C, which is pi. 125 millimeter is 125 10 to the negative 3. So you have 0.125 squared. So you get velocity at C. Right? Now you go, this is a nice thing I like about this book. Not many books do that. Every time he solves a problem, he goes back to the principle. And then he is like upside down. He just start applying assumption. Is it a steady state? Yes. Well, in the real life, is the hydrant flow steady state in the real life?
No.
No, it's most likely transient. Like especially when you start the pump, you see you get those weird noise and complicated fluctuating things. Those are transient. But assume that you reach to a point that you started up and it just the water is coming out. After that, the pattern is same. The velocity is not changing the field. So this is 0. That's exactly what the book says. So you get 0 here, this guy, the density is constant, take it out, and then you get integral over all the faces is 0. And I know velocity is constant over faces, so this guy, you just go to this. So you just say constant velocity at C times the area at C. Now you see dot product. Look at C. The normal vector at C here is pointing this way. Why? Because my control volume is this guy. You see, if this is my control volume, I said the normal vector is always normal to the surface and pointing outward. So it's right here, this way, and in the bottom is this way. But the velocity is this way. So when you dot product NC with VC, what do you get? Sign. Positive or negative?
Negative.
Negative. They're 180 degree different phase, right? So that's you get a negative here. And then VA dot AA. Go here. NA, VA. Are they in the same direction?
Yes.
So the dot product should be positive. What about the other one? Are they in the same direction?
Yeah.
Yes.
Positive. So all of them are positive except C. There you go. Now you substitute number here in this equation. You get this was the velocity at C times AC, negative sign plus velocity at A times AA plus velocity at B times AB is equal to 0. Do I have velocity at B? No, that's actually the unknown problem. And then you solve it for velocity at B. Now you can also find the volumetric rate, but you have to read the question. In the question, if I ask you the midterm, say, when I say midterm, it's going to be next midterm. You have to read, am I asking for the velocity? Am I asking for volumetric rate? Or am I asking for mass flow rate? That's the most frequent one. I usually ask for mass flow rate. Right? So if I ask for mass flow rate, what do you report? Are you going to report dV?
No.
So what do you write? The answer. If I say find the mass flow rate at D.
You do rho times that.
Rho times Q. It's just a definition. That's the thing. You really need to go through the derivation and definition. The derivations and the definition in this course. You can't just memorize the formula because what? Because, well, first of all, you're an engineer, you're not a technician. A technician, you just give him a chart and say, you see this data, cut this part. We had a person in the shop, we had a lathe machine in the shop, and this guy was, he didn't even have high school degree. But all we do, like we give him a chart of diameter and part numbers, and he was like machining his parts precisely to micrometer precision. They didn't have any education. So you're not a chart reader or formula memorizer. You're an engineer. You have to drive everything, but you have to be able to understand why this drives from that, to make judgments. Right? So when I say find the mass flow rate, next term, you know that already you have Q multiplied by rho, 1,000, you get 997 kilogram per second. You multiply that by 1,000. And if the density, well, you have to be careful. The density may not be 1,000. If it's an oil, like we have another application, the density is not water. Water is 1,000. Then you multiply with the density of the fluid. Next problem, let's say, this machine, we got like a heater inside, and the air is coming with a known velocity, the diameter is known, so the mass flow rate is known at this point, if the density is known, right? And then it says find the velocity at the output. Now again, you start from here. Is it steady state? Assuming that, you see, when you turn on this machine, there are going to be some very complicated pattern. In that case, you have to consider that. But assume that you start this machine and the air is coming here and already filling all these pipes and leaving out. Right? And then after that, the pattern is same. Do I have change in the pattern after that point? After the air coming here and goes through the spiral and passes this point. Do I have change after that? No. So it's what? Steady state. So this is 0 after that point. Now I go to this integral. Well, the velocity over each phase is the same, but is the density over each phase same? You have to ask. Well, look, it says we are heating up this. So here is the equation of the state. I write it here. P is equal to rho RT. P is equal to rho RT. That means rho, the density is what? P divided by RT. Now, if you heat up this gas, you already know the density will change. So you pay attention here. If you have a density rho A at this cross section, when I apply heat here, it's going to mess it up, right? So the density when you reach to B, because I changed the temperature, it's going to be something different, right? So when I evaluate this integral, I know that this term is 0, but this term is not 0. Integral over all faces, rho v dot n yes. This is not 0. So when I have continuity equation, this entire thing is 0, right? I have to expand this integral. Let's expand it together. Let's start from here. Right? I get what? Because the velocity approximation, again, you go back here, etc. For air, this parabolic effect is not very significant. I most likely have a constant velocity, so it just be constant. But look, the density in this case, in this cross section, is rho A. And here is rho B. So I cannot just take it out and say 0. So I have to evaluate this integral over all the faces. So let's say we have 3 faces. One here, face number 1. The other one is all the wrapper around this. Face 2, and then face 3 at B. Right? So that this pipe, which is my control volume here, is enclosed by 1, 2, 3 faces. And then I evaluate this integral over each face. So it's going to be integral over S1, or call it SA over A. SA, rho V dot N ds plus the next integral S, call it the spiral, right, over the surface of spiral, rho V dot N ds plus integral over the final closing face, which is B, SB, rho V dot N ds. This sum, according to continuity, must be 0 because it's total change in the mass of system. Right? So what do I get for this step? Tell me, what's the direction of velocity on the wall? You see?
Everywhere.
Everywhere is what? This is the normal at everywhere, and this is the velocity. Everywhere at the wall in this spiral pipe, what's the velocity and normal relation? They are
0.
orthogonal. So the dot product is what?
0.
0. So this entire thing is what?
0.
0. So you get that and this. Now, here, V dot N over A. What do I get for V dot N over A? N is this way, V is this way, V dot N is what?
Negative.
Negative. So it's just negative. This guy becomes rho, and then VA, and it's negative. Now look, rho is not just rho in the entire fluid. It's rho at what? Point A, because after this point I heat it up, and rho will change at that point, according to the equation of state. You see that? So rho A. So rho A VA and times the area at A. Why? Because this S, when you take the integral, after you take the integral, it's going to be V times S. Right? And then finally this term. What do I get for that? Please, Raven?
Rho B, VB, AB.
No.
It'd be
Say that again one more time. Yeah.
Rho B,
Yeah,
VB, AB.
that's right. Positive or negative?
It'd be positive.
Positive. That's right. Quiz waiver. You see, always hunt for quiz waivers. They're very, very random, unexpected. The only way you can hunt it is to fully listen to what I say. Right? So look, how did I get that? Well, you just come here and say, I want to validate integral over this. I know the velocity is same direction with n, so v dot n is what? Positive dv. Right? But as I take the integral, there is the AB, and then the density at B is not a rho, it's rho at B. So put them together, what do you get? You get right here, negative rho A, VA, AA, plus rho B, VB, AB is equal to 0. That's what you get. So the answer, the way the book is solved, again, he starts with the general conservation laws, which is here, and then he goes to the assumption, is it transient? No, 0. And then you evaluate the integral, and then you get the same relation. You put a number, then you just find this relation between rho A and rho B. And now you can apply the knowledge you obtained from the previous chapter, equation of the state P is equal to rho RT. And then when you apply that relation here, you get P at A, you have a relation here, you put the temperature, because the question is giving you the temperature and density at and then you get the ratio between rho A and rho B is equal to 1.60. Put it in this relation here, and you get Vp is equal to 10.7 meters per second. We're just playing with the equations. Now in the midterm, I may just give you this in the next midterm. And I say, well, consider the velocity here is parabolic. It's not constant. Let's say the velocity here is like this. You see, you have a relation. You see the cursor? Like that. And solve it if the velocity is parabolic. Then you start from here. What do you get? 0, not transient. Here, what do you get? You get something like that, right? This is 0 again. You get this, but when you evaluate this integral, you cannot simply say v dot n. Take it out of integral. That's what I did here. You have to evaluate the integral over that surface. And if you can't evaluate the integral over that surface, because this was in the calculus, unfortunately, we don't have time to help you. The only way I can help you is you come to my office and I practice individual with you. There is no other way. You don't have time in the class to go over the very basics. Next problem. So basically, we already solved, I think, 3 more problems last class. We also had a moving control volume. So I think that's enough for conservation of mass. And now we want to go over conservation of momentum, chapter 5. So let me erase this. So I do not erase that. So next chapter after conservation of mass in your book is the energy equation, all right? So you have conservation of mass, and then he goes to energy equation, and then he goes to momentum. I found it to be a little bit distracting if you go from conservation of mass to the energy, because that's not the way the Navier-Stokes equation even is written. The Navier-Stokes equation is written like this. You have conservation of mass, which you already have it. Conservation of mass, and then you have conservation of momentum, and then you have conservation of energy. These all together, they constitute something called Navier-Stokes equation. So we go after conservation of mass, the most natural choice to go is conservation of momentum. But your book doesn't do that. Your book first goes to here, and then it goes back to here. But I want to do it this way, the other way, the normal way. So we go conservation of momentum. After we do momentum, then we do energy. So we come back. We first go to chapter 5, and then we come back to chapter 4. And the way we do it, because we do the general form, we do first Navier-Stokes, and then from Navier-Stokes we go to Bernoulli equation. In your book, he does first Bernoulli, and then a lot of redundant derivations, and then he goes repeat the derivation in the next chapter to get Navier-Stokes. It's better, more precise for you to go to the more accurate and more compact. So let's start with conservation of momentum. So where should I start? I go back to the previous lectures. And I know I had this relation, the total derivative, that will be d dt was local derivative plus, so this was the volume, plus the surface v dot n ds parameter. And I said in the placeholder, this box, this is just a dummy placeholder. You just substitute things, like if I have mass, right? Mass is what? Rho v, right? So if I take mass per volume is same, which is density for the entire thing, you just plug in rho, and then you get what? Plug in rho. You just say the sum, the total derivative for control volume must be equal to 0. Why? Because it's conservation loss. The mass is not destroyed. We had this long time ago. Now, instead of rho, let's substitute momentum. Now, before we substitute momentum, I have to define what the momentum is. This is generic. Alright? So before I substitute the momentum, we have to talk about what the momentum is. Now we go back to Newton's laws. Newton's laws, it says, the second law of Newton, sum forces is equal to ma. This is so vector force, and this is a resultant force on the system is equal to mass of system times the acceleration of the center of mass. Yeah, how many of you guys didn't have dynamics? You didn't have dynamics? Okay.
We should have done. I haven't.
Yeah. All right. So, what about vector statics? Everybody has vector. So here is the thing. You see, this classification is just not very different. So when we say vector statics, we're talking about this one. When we say dynamics, it's talking about this one. And if you know the 5 steps, system, FED, equation, solve, verify, you don't have any problem between vector statics and dynamics, except in the dynamics you have to have inertial force on your FED. The way you put it, you just plot vector statics, but you put the opposite direction of inertia. And then the problem becomes vector statics. Right? If you haven't studied that way, you really need to go back and study in unified form. Because all these courses are just the same. You just look at a special instance of each one of these. Now look at this equation. This is this is simplified version. The actual version of Newton's law is sum of forces is equal to, you see, this is dv dt, right? Acceleration is the time derivative of the velocity. But if you take the mass inside that, so you have ddt mv. This is the actual momentum equation. Now in three-dimensional space, I want to ask someone, do not answer it. In three-dimensional space, how many equations is that? 1, 2, 3, 4, or 6? This one, like so. In three-dimensional space, how many equations is that? So, how many equations in 3D? This equation by itself. What is this? What is this?
Sum of forces,
Which is?
vector.
Vector. In 3 dimensions, how many information do you need to express a vector?
3.
3. So this is just 3 equations. It's not 6. This is just 3 equations. It's not 6. So it says sum of force in X, momentum in X. In fact, you can write it like this. You can write this as sum force in X is equal to ddt mu. Sum force in Y, ddt mv, and some force in Z, V dt, M W. Why? I mean, I should not explain this to you, but I'll just do it. I said we should double check to each other. I'll just do it over and over. This is something you should know it by now. The way you drive this one, this is, you just say F, sum of forces is what? Sum of forces is sum of force in X, I, plus sum of force in Y, J, plus sum of force in Z. Okay, it's for left hand side, and for right hand side, you have V, dt, mv. Then you substitute V, the relation. So you have V dt, m times, for u, V, right, u times I, plus V times J, plus W times K. All right? Now simplify it. Take it in, so you get V dt, mu, I, plus V dt, m, V, J, plus dt, mw, k. So look at this. That's the end result for that, and the end result for force. Now, according to Newton's law, these two are same, are equal. These two are equal. It's called Newton's second law. We usually go with the acceleration, but when you take the correct form, they define this as momentum. So this is called momentum. They call this momentum, right? So when you write it in a vector form, that little guy right here is three equations. It's not just one line. It's not one number. If you in the midterm, if you just write one number, you get 0. I don't even grade the rest of it. That means you've never understood it. You've never practiced it. This guy by itself is three equations. How? Here, force is this, moment is this, make them equal. So the x component, after you make them equal, the I, the coefficient of I, which is these two guys, they are same. The coefficient of J, which is these two guys, are same. The coefficient of K are equal, same. Vector identity. So that is your momentum equation. Now, I want to apply this to my control volume here. You see, the dummy, the place order here. So let's do that. This needs to go up. So, as you remember, when we put mass here, we didn't put m, the mass, we put rho, which was the mass per volume, the normalized mass. It was actually mass, but it was normalized per volume. If I normalize my momentum by volume, what do I get? If I normalize mv, yeah, times volume, what do you get? Rho times velocity. So the one that I plug in to my generic relation is rho v. So let's do that. So I plug in here, starting with the left side, v, the total derivative of rho v dt is equal to. Then you go, and let me use a clue. From this relation, you get partial T, the volume integral. So what should I put here? Rho v. Vv. And this V is not velocity. That's the reason some books, they have problems with the volume and velocity. They put a dash on it. So this over the closed line. Plus the surface integral What should I put here?
Rho B.
Rho V. And then it also has a V dot M by itself. And we talk about that a lot. Yes. So the total derivative, time derivative of momentum, is the total derivative time dependence, total time derivative of momentum. What's the total time derivative of momentum? Go to Newton law. The total time derivative of momentum, dV, rho v was what? Put it this way, mv. What was that?
0.
Newton law. We just wrote it.
Momentum is conserved, so there's no change.
No. Newton law. I just wrote it, I just erased it. Sound force is equal to what? ddt mv. Right? I use the lowercase t, but it's the total derivative. Some books use lowercase, some books use uppercase. So the total derivative of momentum is what? Is sum of the forces on an object. If the sum of force on an object is 0, we have conservation of. I mean, if you look at in the total view, like this is conservation, because some momentum is some forces, right? So this integral must be equal to what? Sum of the forces over the control volume. Now, drive this at home, pay attention. Next class, I'll be starting with this and drive a relation for some forces on the surface of the. That's exactly. After you do that, you get the full momentum equation.